Hello, and welcome to Engineering Tripos Part 2B 4F12 Computer Vision. In this series of 2 lectures, we'll be learning about the many applications of deep learning to problems in computer vision. In this first lecture, we will discuss the motivation and mechanisms underlying all neural nets as we look at the workings of multi-layer perceptrons. Artificial intelligence, or AI, is able to do some amazing things when it comes to understanding images. Here is an example of AI providing dense captions for an image, which includes both finding objects in the image, like the train, the tree, or the puddle, and then describing them using natural language. While these sorts of tasks are trivial for human beings, they have been out of reach for computerized intelligence until fairly recently. It is perhaps because we associate things like describing the scene in an image or recognizing objects with a uniquely human intelligence that the ability of computers to do the same makes them seem intelligent in the same way. However, as we will see over the course of these lectures, just as an aeroplane is not a bird, these algorithms are not machine brains, but are rather simply the repeated application of linear algebra to inputs to produce an output. By the way, if you want to try out dense captioning on your own images, you can try out the Microsoft Dense Captions API by clicking on this link. The only things we have encountered in nature that are capable of intelligence are animal brains, and those brains are made up of millions upon millions of neurons. As such, a good starting point in building artificial intelligence is to try to create an artificial neuron. The ways in which neurons work together involve complex interactions between electrical signals and neurochemistry that are very much outside the scope of this lecture. That said, for our purposes, it's important to understand 3 key concepts. First, a neuron has both dendrites or inputs and axons or outputs, which connect it to other neurons. Second, a neuron will produce an exciting or inhibiting signal along its axons based upon activations from its dendrites in a non-linear way. And finally, each dendrite contributes to whether a signal is produced in different proportions, which change over time. We will focus on these 3 principles and how to use them to build a simple mathematical model of a neuron. The perceptron algorithm was invented in 1957 at the Cornell Aeronautical Laboratory by Frank Rosenblatt, who you see here on the right. It was designed to be implemented in hardware for the purpose of image recognition and was the marvel of the age. On the left here you can see the wiring for the Mark I. The New York Times reported the perceptron to be, and I quote, "the embryo of an electronic computer that the Navy expects to be able to walk, talk, see, write, reproduce itself, and be conscious of its existence." So just in case you were wondering, the AI hype machine has been there from the very beginning. Anyway, Rosenblatt based his designs upon earlier theoretical work by Warren McCulloch and Walter Pitts in 1943 on the threshold logic unit. The idea in both cases was to create a simple mathematical model of a neuron. In the case of the perceptron, this model was then expressed in hardware. The entire machine represented a single neuron with 400 inputs taken from a 20 by 20 image used to create a single binary output. While Rosenblatt's perceptron filled most of a room, we can represent it using a single equation, which you can see here. An input vector x is multiplied by a weight vector w, and the result is passed through a step function. The result indicates the predicted class. What made the perceptron so exciting and revolutionary is that the values of w were learned from the data. The system quite literally learns from its mistakes. It aims to minimize the perceptron criterion, which is a sum over the misclassified examples m. When the perceptron made a mistake in classifying an example, the operator would press a button, and the weights would be updated by either adding or subtracting a scaled version of the input, depending on whether it was a positive or negative example, respectively. Here we see a 2-dimensional binary classification problem being solved by a perceptron. The green line represents the weights of the perceptron, and the magenta circle highlights the current data point. Each time the algorithm misclassifies a data point, the weights will change and the line moves. The model arrives at a good solution after misclassifying a single example, and all it takes is a second misclassification before it has solved the problem. The original perceptron worked on 20 by 20 black and white images. We can simulate this using the MNIST dataset, which has played a pivotal role in the development of neural nets. It consists of handwritten digits gathered from 250 individuals, resulting in 60,000 training images and 10,000 test images. Perceptrons can only be used to solve binary yes-no problems, so we'll take the images from two numbers and train it to differentiate between them. This animation shows the perceptron learning to discriminate between images of ones and images of zeros. Every time it misclassifies a 1, it adds its pattern to the weights, which we see in the middle represented as an image. Similarly, every time it misclassifies a 0, it will subtract its pattern from the weights. Rather quickly, it reaches a point where it can correctly classify the majority of the test images by allocating positive weights to the center of the image and negative weights in a ring surrounding the center, as you can see here. On this slide, we see the same thing again, but for 2s and 5s. It is a more difficult problem as there's not as clear-cut a solution as there was for the 1s and 0s. It makes progress, but each time it updates the weights to account for one misclassification, it creates others. That said, this is promising, but we are quite limited by the fact that perceptrons can only solve two-class problems. As I mentioned earlier, a perceptron is a model of just a single neuron, and a brain contains billions. If we combine several perceptrons together, we can solve more complex multi-class problems using a one versus all approach, where each individual perceptron is tasked with outputting whether an input belongs to a single class or not. The formulation changes slightly. We now have a matrix of weights, one row for each perceptron. Also, to make handling and representing data easier, we will explicitly learn a separate bias, which you see here denoted B. This produces a vector output, and each index in that vector is a binary output indicating whether the input example belongs to a class. This works for some inputs, but as you can see here, we now have the problem that two perceptrons can both fire for the same input. We need to change the activation function f so that it can indicate relative firing strengths for different perceptrons. While we want the activation function that we choose to indicate relative firing strengths of perceptrons, we don't want to lose the nonlinearity, which means we want something that functions like a soft step function. Here are two possibilities, the hyperbolic tangent and the sigmoid. Both of them saturate, meaning that they asymptotically approach a minimum and maximum value, and also have a smooth crossing between these values at 0, like the step function. We can use either of them, but for the time being we will use the hyperbolic tangent, as it most closely mimics the step function from the original perceptron. We are not done yet, however. How do we take a vector of activation values and interpret them in a useful way? One approach is to transform the activations into a conditional probability distribution over the classes. The resulting distribution Q will reflect the probability that the class of an input X is the one predicted by that class's neuron. Q will need to sum to 1 and will need to reflect the relative activation strengths between the different neurons. We can use the softmax function S to produce a Q with these properties, as you can see here. However, now we need to replace the perceptron criterion as well. How do we measure how good Q is? In our case, we know what the correct class labels are, and that translates into knowing the true distribution P, which will be 1 for the correct class and 0 elsewhere. This means we can use the cross entropy as a measure of how good Q is. The cross entropy is a combination of two measures, Shannon entropy and the Kullback-Leibler divergence. Entropy measures how much information we gain from sampling a distribution. In the case of our target distribution, this value is 0. The class of the training data does not change and is entirely known. The Kullback-Leibler divergence measures how likely samples drawn from Q would be mistaken for samples drawn from P. In our case, it will penalize distributions which predict the wrong class. Just as with the perceptron criterion, if we minimize the cross-entropy, we will solve the classification problem. Furthermore, the more incorrect a prediction is, the more it will be penalized, similar to how the perceptron only learns from its mistakes. But how do we minimize the cross-entropy? You may recall learning about a way to use the first derivative of a function to find its minimum using a technique called gradient descent. By calculating the direction and magnitude of the function's gradient, we can take steps, governed by the learning rate eta, towards a local minimum. In this animation, you can see how the derivative with respect to x can be used to find the value of x, which minimizes y, for different learning rates. So that's it. We have everything we need now to train our multi-perceptron. We can write a single equation, often called the loss equation L, which we can use to find the values of w and b, which solve our classification problem. The loss is expressed as the expected cross-entropy over the data set. However, to make things simpler, we'll look at a single data point from this sum. To use gradient descent, we need to find the derivatives of L with respect to w and b. To do this, we will use the chain rule, starting with finding the partial derivative with respect to y. We begin by using the derivative of the logarithm. However, we immediately run into a problem because the softmax contains a sum in the denominator, which means that the derivative will be different depending on whether s of k is equal to s of I. That is why we have to separate out the derivative of s as you see here. That done, we can start simplifying. Because we know that t sums to 1, that sum goes away, and we're left with the simple result that the derivative of the loss with respect to y is the difference of the softmax with the target distribution. Now we turn to the partial derivative of y with respect to h, which is the derivative of the hyperbolic tangent. Via the chain rule, we now have the derivative of the loss with respect to h. From here on in, we're going to be working with matrix calculus, so we will have an easier time if we represent these partial derivatives as a vector that we'll call delta. Anyway, we can now take the derivatives of h with respect to w and b, multiply by delta, and we have an expression for the update step of the multi-perceptron for a single data point. Of course, during training, we'll need to generate these partial derivatives or gradients over all the data points. As you can imagine, for larger data sets, this could be ruinously expensive. As such, it's common practice to estimate the gradient by looking at a randomly selected subset of the data, called a mini-batch. The resulting gradient will be a biased estimate of the true gradient, but in practice this has little to no effect on convergence, provided the step sizes are small. Because the update steps are randomly biased based upon the mini-batches, we call this process stochastic gradient descent. Before we proceed, let's talk for a bit about data. I've thrown around some words so far like training data and test data. What do they mean? Well, all machine learning depends on data of some kind to learn from. In the case of the classification problems we're currently looking at, this data consists of input-output pairs. When we're training a model, we ultimately want it to do something useful. As engineers, you will want to incorporate AI into larger systems, and as such, will need to estimate its performance on new data which has never been seen before. This characteristic of an AI system to work on unseen data is known as generalization, and it is very difficult to predict or measure. However, by careful data usage, we can increase the likelihood that an AI system will have this necessary property. First, we divide our data. The training data is the data the network gets to see and that it uses to train. The validation data is just like the training data and is used to learn the hyperparameters of the system. For a multi-perceptron, this may be the learning rate or the batch size. The test data, however, is different. While it looks similar to the training data and validation data, it must be set aside and never used. Ideally, it is controlled by a third party and evaluated rarely. It is the AI system's performance on this test data which is the true measure of how well it performs in general. This is the source of the two commandments of machine learning. Thou shalt not train on the test data. Thou shalt not determine hyperparameters on the test data. However, there is a fourth kind of data. Held out data is crazy stuff that looks nothing like the inputs the system has ever seen during training. This is a critical part of preparing an AI system for usage in the real world because rarely, if ever, does the real world look exactly like your training data. With all that out of the way, what are the results? Well, here's a three-class or trinary classification problem. The network has three perceptrons, one per class. The points in the current batch are colored in. You can see the weights and biases for each perceptron represented as a colored line. Note how each one learns a one versus all line separating its class from the others. Here we have the multi-perceptron learning how to classify handwritten digits. There are 10 perceptrons, one per digit. We can visualize their weights as images, as you see in the middle. Each mini batch on the left updates the weights, until eventually the system is able to do quite well at recognizing all 10 classes of digits. One cool side effect of our multi-perceptron is that it can express uncertainty. As we sweep from the top to the bottom for the binary problem here, we can see how the system becomes increasingly uncertain of the label the nearer we are to the classification boundary. Multi-perceptrons are really neat, but they have one very real problem that they share with perceptrons. They can only solve linear problems, in which classes can be separated by a linear decision boundary. Here are two non-linear problems. In both cases, there is no possible line that could separate the data, and thus there is no possible solution. Both of these problems can be trivially solved, however, using a technique called feature engineering. A human expert looking at these problems can design a feature which makes the problem linearly separable. In the case of the XOR problem on the left, we simply multiply the x and y coordinates together. For the bullseye, we use the radius. Feature engineering is great. Don't let anyone tell you differently. With problems like this, where an expert can inject their expertise into the problem as an additional source of data for the learning algorithm, it can be the difference between a working system and a failed project. However, as inputs become more complex, it is much more difficult to engineer useful features. In these cases, it would be useful if there were a way to learn the features automatically from the data. It ends up that we can use multi-perceptrons to solve this problem too. One multi-perceptron will solve the feature engineering task, and then another will perform classification. The intermediate or hidden layer is often called a fully connected or linear layer, and the resulting sequence is called a multi-layer perceptron or MLP. At this stage, I want to introduce a graphical notation that I'll use for the rest of this lecture and extensively in the next. Each layer is represented by a vertical rectangle, as you can see here, and the relative number of neurons represented by circles. The annotation at the top indicates the kind of layer, F for fully connected in this case, and then a number in brackets indicating the number of neurons. Underneath, we have the output dimensionality of the layer. Finally, if there is a transform performed on the output, for example, a nonlinearity like the hyperbolic tangent as we have here, it's denoted as a superimposed circle. As the neural nets we examine become more complex, this notation will help you to get a sense of its structure at a glance. So, how does our MLP do at solving the XOR problem? This network has a hidden or latent space with a dimensionality of 3. Each input data point on the left is also plotted in the 3D latent space. The classification output of the network is shown as colored pixels on the left. As the MLP trains, it uses its feature perceptrons to place the input points in the 3D space so that a linear decision boundary, in this case a plane, can separate them cleanly. We have a similar story with the bullseye problem. The network uses the extra dimension to embed the data such that a decision boundary can cleanly separate it. Understanding the latent space is a critical part of understanding how MLPs work. In this animation, we take a single blue data point from the dataset, which we highlight here as a large magenta square, and change its label from blue to red. We then backpropagate all the way through the network, keeping the weights and biases fixed to the input data point itself, and update its values. In essence, we are asking the network to change the input data point into what it thinks a point of the opposite class is. As you can see, the network moves it out of the high probability blue area and then shifts it slowly through the no man's land between the two classes before finally placing it in the nearest cluster of red data. Note in particular what happens to the point in the latent space as this happens. So, how does an MLP do on the MNIST task? Here's a sample network. The input is a flattened 28 by 28 image for a total of 784 dimensions. We create features from these inputs using 64 feature perceptrons, and then these features are used to classify the images into the 10 classes. Unlike the multi-perceptron, the MLP is harder to analyze. The feature weights start as random noise, but eventually settle into what appear to be different kinds of strokes. However, the way in which those strokes are combined to create classifiers is very hard to understand just by looking at the weights in this way. That said, the result is more accurate than what came before. What happens if we play the same trick as we did with the red and blue points, in which we update the input data by propagating the gradient back through the network to the input? Given the size of the input space, we will add an additional constraint, which is that the altered input should be as close to the original as possible. Here we see what happens when we change the label of a 4 to be a 9. It isn't quite what we would expect. The network adds a bit of ink in a few places and removes it in others. The changes are barely perceptible. However, the resulting change in the output of the network is dramatic. Without changing the input all that much, the network becomes as certain the input is a 9 as it previously was that it was a 4. This can be thought of as a form of attack. An adversary with access to the original network could change inputs in subtle ways, such that the network acts completely differently. This is an inherent weakness in networks of this type and highlights both the importance of testing where networks fail and of increasing the quantity and variety of training data. As this lecture on MLPs comes to a close, let's look at some tricks of the trade that are used when training neural nets. The first is a trick to speed up stochastic gradient descent called momentum. When making an update, it is often the case that it is in the same direction as the past few updates. In these cases, momentum, which functions as a moving average of the past few gradient updates, can speed things along. Similarly, if the gradient changes rapidly, it can slow the network down. The result is often considerably faster convergence on the local minimum and, due to the moving average acting as a low-pass filter, a smoothing effect over noisy stochastic gradient descent updates, which can allow for a smaller mini-batch size and thus faster training. Another common problem with gradient descent is that the ideal learning rate changes over the course of training. Specifically, as the network nears the local minimum, it needs to take smaller and smaller steps to get the best possible weights. One way of achieving this is by changing the learning rate during training, either via stepping the learning rate over fixed intervals or via exponential decay. Sometimes the gradients of the loss function become very large as a result of large errors. These large gradients make equally large changes to the weights, resulting in further, larger errors. This phenomenon is referred to as exploding gradients and can be solved by reducing the learning rate. However, the process of learning how large or small the learning rate needs to be is largely one of trial and error. The Adam algorithm provides an alternate approach. Instead of using the raw gradient, Adam uses the first and second moments of the gradient and constructs a gradient update which is guaranteed to be bounded. This greatly stabilizes training without requiring problem-specific knowledge, making it a very popular choice, especially in the early stages of model building. Another problem is the vanishing gradient problem. Both the hyperbolic tangent and sigmoid activation functions can have the problem that they reduce the overall magnitude of the gradient as we add layers to the MLP. In the case of very deep networks, this can be quite dramatic, as we see on the left. Thus, many modern neural nets use different activation functions, like the rectified linear unit or ReLU, which do not have this effect. Even though the gradient of the ReLU has a discontinuity at 0, in practice it can be used safely to train neural nets. At the moment, our input transformations are performed by a fully connected layer, where each neuron in the output is connected to every input. While these layers are very expressive and can handle a wide range of potential inputs, they also require many parameters. In our example network from earlier, trained on MNIST, the first layer from the 784 pixels to the 64 feature perceptrons requires 50,240 parameters. As a rule, the more parameters you have, the more capacity your model has to overfit to a dataset through memorization. Remember, we want to generalize, and so a model that simply memorizes the training set is not going to do particularly well on the test set. As such, we want to reduce the number of parameters in our network if possible. Here is where injecting human expertise into the system comes into play. Natural images have a lot of structure. On the left, you see samples from the space of all possible RGB images. If I were to let this play long enough, you would see a photo of anything you can imagine, from long-lost treasures to what you had for breakfast yesterday. However, the overwhelming majority of samples will look like this: noise. In the middle, we see some actual photographs, and on the right we see those same photographs, but with the pixel values randomly shuffled. To an MLP, all three of these look exactly the same. The neural net has no concept of image structure and has to learn that along with everything else in order to solve the problem. That's why it needs all of that extra capacity, because in addition to learning how to classify digits, it also has to learn how to see, in some sense. In the next lecture, we will see how we can use ideas from earlier in this course to help the MLP to work with image data in a more efficient and natural way. Thank you for watching today. Whether you're a student at Cambridge or just a curious soul looking to learn more about deep learning and computer vision, I hope you find it helpful. You can find a link here to the next video in the series, in which I discuss convolutional neural nets and their many applications. In the description, you'll find a link to a GitHub repo containing Jupyter notebooks and Python scripts that act as companions to these lectures and can help you to continue learning at your own pace. You will also find references to various papers and articles describing the algorithms and techniques I mentioned in this lecture. Have a lovely day.